So Dr. Vedan,
Is the
situation better there?
like it's improving?
The connection?
No, I mean to say the
pandemic condition.
Oh yeah. In New Zealand, in New Zealand, it's fantastic. It's fantastic. I mean, we don't have lockdowns. Or anything. So you know, we're kind of lucky. In this sense. But we're hoping that the vaccine was approved to. I'm hearing myself. Is there?
oh,
Is there?
it's echoing.
It's echoing. I think all our voices.
Krishna Mani, can
Can you please check it?
Yeah, there is echo for everyone's audio.
I guess.
Just give us a couple of minutes. We are fixing this issue.
Sure. No problem.
Madam, still is there echo?
Hello?
Still it's there echo?
It's
Echo is
fine
there?
now, I think.
It's fine now, I think.
Fine. Okay, ma'am.
No, it's still echoing.
No, it's still echoing.
Still. Okay, ma'am. We are. Ma'am, I think everyone mute, then I think it will be fine. Okay, so let's see. Okay, once we start the sessions.
Okay, but the speaker, whoever is
the speaker,
Okay.
I request everyone else to mute
themselves.
Hello? Hello, can you hear me?
I can hear you. Yeah.
Yes, ma'am.
I think still that. Yeah, it's still echoing. I'm not sure why.
I'm not sure why.
Have you opened any other system other than this? Is it opened in any other system? Simultaneously?
Paramita ma'am.
Yes.
Yeah. So I'll unmute. I'll mute myself. Tell me whether echo is there or not.
Okay. Yeah. Hello.
Yes, ma'am.
Yeah, it wasn't echoing now.
Okay. Only when I on, it is getting echo.
Yeah, I think it's multiple systems simultaneously. If it is on, it will echo. So I think Dr. Alagiri, when you have to mute yourself when anybody else is talking. That's it, I guess.
Yes. We'll do that one, ma'am.
Sure. Okay, then we can start the session.
Hello, ma'am.
Yeah, we can start the session.
Okay, sure, ma'am. Sure, thank you.
Yeah.
Ma'am, whether you can see my screen? Screen is visible. Hello, ma'am.
You please make it in a slideshow.
Okay, sure, sure.
Visible.
Sure. Can you hear me, ma'am?
Yes, yes, please.
Okay,
Yes,
thank you,
please
sir.
continue.
Okay, so good morning to everyone present here. Myself, Dr. M. Aragiri, Assistant Professor in the Department of Physics and Nanotechnology, SRM Institute of Science and Technology. I welcome you all for the parallel session on nanocomposites and catalyst, nanobiotechnology, nanotoxicology, and medicine. In this session, we have 3 invited lectures. Now, I am pleased to introduce the chairperson of this session, Dr. Paromita Chakrabarty. Dr. Paromita Chakrabarty, working as a research professor in SRM Research Institute, SRM Institute of Science and Technology. Professor Paromita Chakrabarty, Madam research interests are multimedia movement of persistent organic pollutants in the hotspot of Indian cities, long-range atmospheric transport of persistent organic pollutants, quantification and ecological impact assessment of emerging contaminants of concern in riverine and marine environment of India, and cost-effective remediation techniques for emerging organic contaminant in soil, sediment, water, and wastewater. Professor awards and achievements are Young Scientist of the Year Award for 2014, awarded in International Conference on Environment and Ecology, Early Career Chemist by the 2015 International Congress of Specific Basin Societies, Eminent Young Scientist of the Year 2015 for Environmental Science and Technology, awarded in international conferences on environmental and ecology, and Distinguished Young Scientist of the Year 2016 for environmental conservation. With this short introduction, now I would like to hand over the session to Professor Paromita Chakrabarty. Please, madam.
Thank you, Dr. Alagiri. Good morning, everyone, and I welcome you all for this very interesting and important session. Dr. Alagiri, if you can mute yourself.
Oh, sure, ma'am. Sure.
So, I welcome you all once again. I don't know, Dr. Alagiri, it's still echoing.
I'm muted. Muted.
Okay. So let me introduce the first speaker of the day, Dr. Vedran Jove. Dr. Vedran Jove completed his PhD from University of Auckland. And strikingly important part is his postdoctoral experience, sources for the National Laboratory in California, 2014 to 2019, use of X-ray radiation to study the fundamental electronic structure of material for renewable energy production and for potential use the electronic industry. Dr. Vedran has several peer-reviewed publications, and his research interest lies in the development of materials and processes for electrocatalytic hydrogen production and conversion of C1 molecules to higher value chemicals. So I welcome Dr. Vedran Jove to deliver his on direct nodal lines and advanced surface state in the functional oxide titanium oxide. Dr. Vedran, you're most welcome for your lecture.
So I just test my microphone. Can you hear me?
Yes.
Okay, great. And I can't hear an echo, so I will share my screen.
Sure.
Okay. Let me just set it up, and it's just a Sorry, one moment. My PowerPoint presentation decided to close itself in the worst moment.
Yeah, it's fine. You take your time, no problem. Yeah.
Here we go. I think it should wake up. Okay, it's awoken. So now okay, now I'll share it. Share screen. Okay, can you see my?
Yes, sir. Yes, sir.
Yes. Screen is visible. Yeah. Great.
Okay, and what can you see? Can you see a proper PowerPoint, or do you see the presenter view?
We can see the proper slideshow view. Yeah. Perfect.
Okay, great. Okay, thank you so much. So I will I will give you a presentation on the work I did during my time at the at my postdoctoral time at the Advanced Light Source Synchrotron in Berkeley, California. And the work is direct nodal lines in the flatband surface state and the functional oxide ruthenium dioxide. So before I get into an outline, let me just start by highlighting some of our key findings from these studies. So these results were some of the first reports of bulk direct physics in a functional oxide. So this ruthenium dioxide, a material with really concrete applications. So using angle resolved photo emission, we observed a network of direct nodal lines at the Fermi surface. And the direct nodal lines, they give rise to what's called a flatband surface state at the Fermi level. It's kind of an unobserved analog of this drumhead surface state predicted for nodal ring semimetals. And this it's kind of a new gateway for study of exotic physical phenomena like unconventional surface superconductivity in some of these materials or long-range Coulomb interactions. And these results kind of established for the first time a link between the fundamental topological properties and the surface functionality of a very energy relevant material. It's a very popular catalyst, gold standard catalyst for water splitting reaction and amongst other processes. And we will try to make this link between the direct nodal lines and these nested hotspots in the Fermi surface to magnetism in this material. So in the first part, I will just show you the experimental setup and the nature of the materials. Then we'll take a look at some concrete applications and identify the chemical and physical properties behind the material's functionality. We'll also take a deeper look into the crystal structure, non-symmorphic symmetry, and its influence on the formation of these direct nodal lines. And then in part two, we'll also take a look at a little bit of a look into the DFT of the electronic structure in this material, and then we'll take a look at the scenario defined by the theory is indeed confirmed by experiments, and we see these observation of these direct fermions. And we'll do this by looking at two types of direct nodal lines, A and B. And in part four, we'll take a look for evidence of a third and unexpected direct nodal line along the XR direction, which produces these direct crossings at the Fermi level. And they serve as anchor points for this non-dispersive flatband surface state. And then finally, in part five, if I have time, I'm sorry, we'll take a look at how it responds, these electronic features, how they respond to doping and loss of coherence in response to the changes in the electrostatic environment of the surface of the material. So let's take a look at the material itself. So these were slightly iridium-doped ruthenium dioxide single crystals grown in Lausanne by the group of Helmut Berger. And they followed a recipe described for a long time in theory. And if you follow this recipe, you will get single crystals of ruthenium dioxide. in about 2 weeks. And then the core level XPS studies showed that at several different energies confirmed essentially the stoichiometry of the material, that we indeed have this slightly iridium doped ruthenium dioxide, and X-ray diffraction confirmed that it's essentially in the rutile crystal structure with the lattice parameters consistent with the rutile dioxide, RuO2. So then a colleague of mine, Simon Moser, who is a professor, now a junior professor at Würzburg University. We were together postdocs at the Advanced Light Source Synchrotron. We together started to study the electronic structure of the single crystals of this material at this beamline 702. It's called Maestro at the ALS. And we performed our measurements on these single crystals. Oh, actually, so it's quite a complex beamline. We specifically, many UHV chambers all interlinked together, so you don't essentially, your sample doesn't have to see ambient conditions. So we specifically worked on the micro ARPAS chamber. We prepared our samples by gluing a ceramic top pin to single crystals, and within the UHV chamber, we hit these samples and they would reveal a perfectly clean surface of the material, and it was highly reproducible. We were exposing these 50 micrometer clean facets of the thermodynamically most stable 110 terminated oxygen terminated surface, and the synchrotron beam essentially in these ultra high vacuum chambers, which were very ultra high. As you see the pressure there, the synchrotron beam was actually on the order of around 20 micrometers or less. So we could really see very tiny little domains of the material, and then you see the geometry of the experiment with respect to the electron energy analyzer and the light coming in onto this 110 surface and how it was oriented. So let's take a look at some of the existing and current applications of ruthenium dioxide and some motivation for this work, and then we'll look a little bit more at the non-symmorphic symmetry in this material and the influence of symmetry on the formation of these direct nodal lines. We'll also take a little bit of a look at the ab initio calculations and what they can tell us. So ruthenium dioxide in many senses falls in with other binary 4D transition metal oxides. It's a good metal believed to be a polyparamagnet. So it's, from the point of correlated physics, it was kind of seemed quite non-interesting. However, in terms of its functionality, it's one of the most important oxides out there and it has quite remarkable electronic ionic conduction properties, favorable thermal and chemical stability in various environments. And so it serves as a very important catalyst for many processes. The 110 surface actually of this, actually in catalysis here, and I highlight here in this Deacon process, which is an industrial process. So this, the significance of the non-symmorphic symmetry in ruthenium oxide was actually recently discussed within the framework of topology and relativistic physics in a very nice paper by Jan Sun and his co-workers. So essentially it tells an experimentalist who wants to measure the band structure of this material, what does this look like theoretically? It tells us that the symmetry considerations in conjunction with DFT calculations predicted what's called the network of Dirac nodal lines close to the Fermi level. And in contrast to the more prominent Dirac and Weyl semimetals, which host fourfold and twofold degenerate zero-dimensional Fermi points, the Dirac nodal lines have a one-dimensional Fermi surface. It's a symmetry-protected crossing of the conduction and valence band along the discrete line in K-space, and it has relativistic fermions close to the crossing point where the two bands meet, and they are essentially typically protected by crystalline symmetries. And in particular, they emerge in systems with inversion, non-symmorphic, time reversal, and mirror reflection symmetries. And they force this protected crossing of the conduction and valence band in K-space. And there are essentially two types of Dirac nodal lines in ruthenium dioxide. There's a type A and B. And the type A Dirac nodal lines, they are first, they have time reversal and inversion symmetry, and in unison with a mirror symmetry, protect a band crossing within the 110 and family of planes. This produces a network of these fourfold degenerate, two-spin, two-orbital, and topologically non-trivial direct nodal lines. And they are outlined here in the Brillouin zone. And then there's a second type of direct, and this is how they look like in Fourier space. And then there's the second type of direct nodal line in ruthenium dioxide. It's topologically trivial, protected by non-symmorphic glide and mirror symmetries. So ruthenium dioxide is essentially a bipartite composition of two sublattices within different ruthenium dioxide octahedra that are related by a fractional translation of half a body length around the 110 plane. And in an analogy with this diatomic chain model, this glide plane effectively doubles the unit cells, backfolds the bands, and then in conjunction with the symmetry properties, it again forms a second set of direct nodal lines in the system, and they are along here in the Brillouin zone. And in the presence of spin-orbit coupling, or in the absence of it, these in the presence of it, these direct nodal lines are supposed to gap, as I showed you in these two simulations, and resulting in the so for instance, it's expected to produce large intrinsic spin hole conductivities, etc. And then the intersections of all of these points are shown here as the hexatuple, the octatuple points, and essentially it's quite a complex band structure predicted by these symmetry principles. So we will see that this scenario presented on this earlier stage, you can actually reproduce it on these samples that we that our collaborators grew by angle resolved photo emission. So first, to identify the planes, the high symmetry lattice planes in the structure of ruthenium dioxide, we employed photon energy dependent ARPES. This is the experimental surface in the 001 plane, and it's compiled from the ARPES measurements in the range of 60 to 800 electron volts. And so you see the unit cells are marked out with the dashed lines. And so the circular spectral contours enhanced in every other Brillouin zone means essentially that they are following the ruthenium dioxide sublattice rather than the primitive periodicity. And this is the hallmark of what is called a non-symmorphic symmetry, non-symmorphic glide mirror plane of ruthenium dioxide. So the black lines are essentially the primitive 3D Brillouin zone there, and the red ones are the non-primitive. Okay. So from this periodicity along the 110 planes, we can identify photon energies at which the ARPES probing sphere cuts the Brillouin zone close to the high symmetry planes. And I showed this in the image on the left. And at these energies, we essentially acquire ARPES surface data sets using the system. And so as illustrated here in the top of panel B, the ARPES hemisphere at 69, you can see where it cuts, and it produces this Fermi surface that contains both the X and R high symmetry points. And then in contrast, at 87 electron volts, the middle one on the right, and at 131, you probing the 3D Brillouin zone close to 110 plane, identical with this GMAZ high symmetry plane, with either the AM or the GZ lines centered in the ARPES map, and I will show you, as I will show you in the upcoming slides. So to confirm this theoretical scenario, which was predicted on the previous slide, let's take a look at the Fermi surface collected at 131 electron volts. So with the direct lattice parameters of that I've indicated here, the black dashed line shows the primitive Brillouin zone markings, and we can identify four main contributions to the Fermi surface. I've summarized these in this little schematic here on the bottom left using the numbers 1 to 4. So first we identify the arcs, which these arcs, number 1, centered halfway between the GM markings. These represent one branch of the direct crossing, and it forms forming this, which I'll show you later, forming this third direct nodal line, which was completely essentially missed by theory. Second, we find the intense spectral features at OP along this MA line. These are intersections of the direct nodal 1 and 2 in the XR momentum plane. and they're complemented by weak features HP along GZ, where the direct nodal lines cross with one another. And then you see this fuzzy horizontal streaks connecting points OP and HB, and they are spin orbit split residuals of this third direct nodal line. And they actually form these hot streaks, which I'll show you in the third, one of the later slides, claimed to be responsible for the magnetic instability in the material. And fourth, you can see this two prominent arcs spanning between features 1, and they're the signature of the flat band surface state. So the ARPES band structure along the high symmetry planes is well reproduced by the spin orbit, the DFT plus spin orbit band structure calculation, following the discussion by Jan Soon on the previous page. And we can then identify these intense features in the Fermi surface. So let me just see where I am. Yep. So yeah, essentially, if you can replicate, you can, sorry, let me just see where I am. So let's take a look at the expanded area of the direct nodal line 2 dispersion along the ML line. It essentially highlights the band maximum at the octatuple point, as you can see in this middle red circle. And if we take perpendicular ARPES cuts, band structure cuts at prominent momenta, shown by these white lines in, we plot them in H1 to H5, they reveal for us the appearance and the evolution of the direct crossing between the OP and A. And the curvature exemplifies this crossing and shows essentially excellent agreement with the DFT prediction that I've shown you earlier. Okay, so yeah, and here we go. So this is the agreement. The DFT was superimposed on the actual experimental band structure. Okay. So, it appeared a little, and now we return now to our main Fermi surface schematic, and let's take we could take a closer look at the band dispersion of direct nodal line 1. Let me just be mindful of the time that I'm taking. Actually, this slide, I may not have time to go through the slide, but essentially does the analogous view of the band dispersion of the direct nodal line 1 along the gamma z direction. And it was actually depicted in these ARPES images, but essentially it's proving what the DFT calculations show. But what I'd really like to show you is this third and unexpected direct nodal line. So as I mentioned, when we inspected the 110 surface plane containing the XR points, we found a third nominally gapped direct nodal line that essentially it wasn't predicted by the density functional theory. And finding this direct nodal line was really tough. We first started to study this material. There was really no ARPES studies on it. So we did a complete overview of the material structure, as you saw from those large KZ scans that I showed you on the earlier sign. And then we took these cuts, essentially, we took Fermi surface maps at 5 EV steps all along the structure, and we analyzed each map individually. And so this panel A is the cut along 69 EV, and the photon energy is essentially probing the brilliance along the 110 plane, containing both the X and R points, which I show you in the top left here. And once again, we have a little schematic which summarizes for us the main features, and we can quickly summarize these before we delve deeper into them. So first and foremost, we observed a double arc structure centered at the X points, and they are the two branches of the direct nodal line that forms the third DNL3. The arcs extend towards the zone center, and are restricted to a very narrow range of photon energies, which you see in the middle here. So essentially, you really had to hit this narrow range to see both of these arcs in the same window. And this is shown in this momentum dispersion curve. And so second, we find these intense spectral features labeled DP in the top left. These are the intersection points of DNL1 with the XR momentum plane. And third, we find these hot streaks that you can see in the top left, and I've labeled them here in the top left. Their intersection with the XR line, with the Brillouin zone boundary, marks these hotspot features in the Fermi surface, and they are actually claimed to be responsible for the magnetic instability in ruthenium dioxide. And finally, you can then see the prominent arcs of the flat band surface state anchored between these Dirac nodal lines. So this is really a surface state, whereas the Dirac nodal lines are bulk features in this material. So next slide. So, okay, so it's my computers. So we can essentially dwell a little bit more into each of the features we saw. Sorry, my computer is going a little bit crazy.
I think Dr. Vedhan is reconnecting himself. So just
I think
couple
so.
of minutes, yeah.
Okay.
என்ன பண்ணலாம்?
Dr. Vedan, are you back with us?
No, I cannot find him in the participants list. I think he's not here.
Yeah, I think he's finding it difficult to
Yes, ma'am. Yes, ma'am.
connect.
Yes.
So we'll just wait for 1 more minute and then
Okay,
move
sure.
to the next speaker. Yeah.
Okay, sure.
I would request the audience to please excuse us. Just 1 more minute, we will wait for Dr. Vedan to come back. Please cooperate with us. Yeah. I think he has some serious issue with the internet connection. I think we can proceed with the next presenter and take back Dr. Vedan once he's back, once he's able to connect us.
Okay, ma'am. Okay.
Yes. And before we go for the next presentation, I would like to mention that each presenter would get 25 minutes for presentation. After 22 minutes, there will be a first bell. And after 25 minutes, there will be a discussion with the audience. So the presentation time is 25 minutes. I'm here to introduce our next speaker, Paul Rosener Rajonia from Nara Institute of Science and Technology, Japan. Paul is a doctoral student here in Nara Institute of Science and Technology, and he also received the Best Student Presentation Award at EM Nano 2019. He works on collaborative work between material science and information science, and today he's delivering a talk on probabilistic machine learning for predicting cytotoxicity of titanium dioxide multi-metal nanoparticles. So over to you, Paul. Welcome.
Hello. Can you all hear me?
Yes, we can hear you. You can start
Okay.
your presentation. Yeah.
Okay. Okay. So, hello everyone. My name is Paul. I'm an information science grad student from Nara Institute of Science and Technology. And today I'm going to present our research on predicting nanotoxicity using a probabilistic machine learning model. Uh, can you see my presentation?
Yes, we can see your presentation. Yeah.
Okay, thank you. Okay, so let's begin. We are living in the era of nanotechnology. We have seen how such a small-scale technology can be applied to several areas, but with its benefits comes its risks. Nanomaterials are potentially toxic, and exposure to this may be hazardous to our health. In this study, we propose a machine learning solution to testing the toxicity of nanomaterials. Using this machine learning model, we can predict nanotoxicity and optimize future toxicity experiments with the hope of reducing the use of animals for testing. To build the machine learning model, we performed a 5-step methodology. The first step is data collection. We used the data samples by Mikolayczyk et al., where in their study, they produced 34 titanium dioxide nanoparticles mixed with various concentrations of at most 2 metals via microemulsion. These metal NPs are silver, gold, and platinum. Each sample has 14 descriptors or features, and each one is tested for cytotoxicity on Chinese hamster ovary cells. They used the half maximal effective concentration or EC50 value as the predicted variable. Then, they applied integral additive descriptors to describe the weighted effect of different mixtures of nanoparticles to the overall property of the cluster. Using DFT, they calculated several quantum mechanical properties such as absolute electronegativity, absolute hardness, adsorption energy, and so on. Once we have these data samples, we proceed to the second step, which is pre-processing the data. Here, we standardize the data per descriptor. Then, we split the data into 3 sets for training, validation, and testing, following a 40-20-40 ratio. And finally, we randomly shuffle and split the dataset for 10 iterations. Moving to the main stage of our research, we now build the Gaussian process regression model. GPR is a probabilistic regression model wherein we fit several functions over the given dataset, and the model returns a probability distribution over these functions. The model is defined by a mean function and a covariance function. In our case, we simply set the model mean to 0 and focus on choosing the best covariance function, otherwise known as the kernel. The kernel is useful for setting the hyperparameters of the model, such as the vertical scale sigma, which defines the vertical span of the functions, and the horizontal scale L, which defines the correlation between 2 points relative to their distance. Different kernels lead to different models. For example, a radial basis function or RBF kernel would yield a somewhat balanced model, whereas using a dot product kernel would return a more simple and much smoother model, which might underfit the data. On the other hand, using a more complex kernel like a periodic kernel would result to a more complex model but may cause overfitting. The GPR hyperparameters are optimized by maximizing the marginal likelihood using a gradient optimization algorithm such as limited memory, Broyden, Fletcher, Goldfarb, Shano algorithm. Given our dataset, it is important to select the best features to produce the best model. As I described earlier, we split our data into training and testing. And during feature selection, we set aside the testing set to avoid any bias that may leak into the model. Consequently, we split the training into a validation set, which will be used to evaluate the model during feature selection. We perform cross-validation wherein we shuffle the split several times. This allows us to use the entire dataset for training and validation. For feature selection, we want to find the subset of features that produces the most accurate model. And since we only have a small dataset and a small number of features, we decided to perform an exhaustive search for the best feature subset. It took a total of 3,472 combinations of 5 out of 14 features, which ran in our computer for around 26 hours. Our program then scores each possible combination of features, and the combination or subset that scores the best is selected. So, how do we evaluate or score the model? First, we use the coefficient of determination, or R squared, to measure the goodness of fit of the model to the data. This metric explains the model variability, wherein an R squared score of 100% means that the model perfectly follows the behavior variability of the actual data. Next, we use root mean squared error, or RMSE, to measure the accuracy of the model's predictions. A perfect score of 0 means that the model predicts the data without any error. Let's now talk about the results. During feature selection, we evaluated the models trained on different combinations of features, and we found that AG concentration percentage and adsorption energy features produce the highest scoring models for both R squared and RMSE. Looking at the top 10 feature subsets for both of these metrics, we can see that most of them include either 80% or adsorption energy. Thus, given these results, we trained the model on 80% and adsorption energy and then tested different kernels. We tested a total of 6 types of kernels: the dot product, constant multiply dot product, matern, periodic, RBF, and rational quadratic. Out of these 6 kernels, RBF has the highest R squared score of 94.32, followed by periodic and RQ. In terms of RMS error, RBF also scores the best, with the least RMSE score of 0.10, again closely followed by periodic and RQ. Comparing our Comparing our model to the QSAR models of Mikolai Sik et al., our GPR model outperforms in both R squared and RMSE scores. Now, let's discuss the possible mechanistic interpretations of our results. By looking at the best features, 80% and adsorption energy, and their relationship with EC50 toxicity, we can see that our model reaches higher toxicity values when absorption energy is low and 80% is high. To explain this effect, let's take a look at how metal mixed TiO2 nanoparticles react when mixed into CHO cell solution. Because of low absolute adsorption energy, the TiO2 cluster becomes less stable, and thus Ag nanoparticles can detach from the TiO2. These Ag nanoparticles can then release ions, which in turn generate reactive oxygen species, or ROS, and this ROS can lead to DNA damage, unregulated cell signaling, and cytotoxicity. So this explains how adsorption energy affects cytotoxicity. But how about 80%? First, among the 3 metals, Ag is the most reactive. Furthermore, a study compared the toxicity of these nanoparticles on zebrafish embryos and found Ag as the most toxic and Au as the least toxic. Finally, let's discuss the advantages and disadvantages of using our GPR model. First, GPR has a built-in hyperparameter optimization via the maximization of log marginal likelihood, and this makes the model consistent and robust even without the need for cross-validation. Second, since the model is probabilistic, we can see the confidence level of the model on its predictions. For example, here, the model has high confidence on predicting samples along the yellow band, which is where our current data samples are in. As we try to predict other samples farther from the center, the model becomes less confident. This information is crucial for high-risk problems such as predicting nanotoxicity because model predictions can have real-life impact. And capturing model uncertainty is a careful approach to such problems. Not only that, because GPR informs us with its uncertainty, we can use that information to direct our next lab experiments. For example, in our current model, we can see that the model is not confident in this area. But this area is where 80% is the highest, and yet the model predicts EC50 to be lower. So perhaps on our next experiments, we can try high concentrations of Ag mixed into TiO2 and then add other metals or use certain techniques that would increase the absolute absorption energy to get lower EC50. Because of this probabilistic information, our model can help researchers optimize their lab experiments. All of these show the power of GPR model. Yet of course, GPR has its own challenges, such as first, selecting the best type of kernel. In our study here, we use predefined kernels from the Python scientific scikit-learn library, but it's possible that the kernels and parameters we use do not match the nature of the data. So without expert knowledge, it's easy to fall into the trap of kernel selection since there are so many possible to choose from. And as we've seen in the results, GPR can be quite sensitive to the kernel choice. Second, GPR does not scale well with large datasets. As the number of samples increases, the computation time and memory costs increase as well. So there's a need to use more complex Gaussian process techniques in order to work around large datasets. Nevertheless, we believe that these challenges are solvable. In summary, we address the problem of toxic nanoparticles using a computational approach. In this study, we designed and built a Gaussian process regression model that can accurately predict nanotoxicity. Given its probabilistic nature, our model can capture uncertainty, which can help researchers optimize their lab experiments. As machine learning increasingly transforms the production and use of nanotechnology, there are inherent risks involved that we must carefully consider. And so with this approach, we want to send a message of caution and carefulness since these technologies can have direct impact to our lives. To the best of our knowledge, this is the first time GPR is used in nanotoxicity studies. So we hope that more nanotoxicity researchers would consider this model in the future. Thank you for listening. I would like to acknowledge the help of our colleague, Dr. Pelicano, and my scholarship aide, ERDT-SEI, for the support. And finally, I would like to thank my collaborators, Josh, Enzo, and my advisor, Ikeda Sensei. Once again, I'm Paul from Nara Institute of Science and Technology. I hope you're all well and safe. Do you have any questions or comments? Just a bit of disclaimer, I'm a data science guy. So if you have deep questions on chemistry or biology, I would have to direct your questions maybe to my collaborators. So thank you for listening again.
Thank you very much. It was really a very, very interesting talk. And given the fact, Paul, that data learning is gaining so much of importance in every field. So to me also, it looked very, very promising. And maybe a lot of modeled output can be obtained before we go for a real-time analysis. I'll take up some questions if we have from the audience. You actually completed very much right before the time. So we can discuss even more if there are more people to question you. So from the audience, from the participants, is there any question for Paul? Any question? Anybody? You can directly unmute yourself and question, or even you can write it in the chat box. I can ask the question on your behalf. So I don't see any questions so far. I have one question, Paul. It's really interesting, and you are using the Gaussian process regression. So when you are talking about the best fit, you are only talking about the model fits, or you are also looking out, in the experimental data and trying to fit both, and then coming up with your understanding. Or is there any limitation in this regard? Yeah.
In terms of the fit, we perform machine learning so that using the data samples, we fit the model accordingly. As for limitations, I guess the model will be as good as the data, because if, for example, you have a noisy data set, the model could capture that noise also.
I see. Yeah, interesting. And is it only for cytotoxicity, or such models can be used for some other applications? You're aware of any other applications where?
I actually, for cytotoxicity, I think this is the first time GPR is used, and we got this inspiration from uh, other material informatics research, such as, I think, band gap prediction uh, uses GPR, if I'm not mistaken. So that's how we got the idea that maybe GPR could be applied here as well.
Yeah, okay. Thank you. I have a question now from Arpita. Arpita Day is asking, how will the predicted values Arpita? How will the predicted values matches the real data in your study? Arpita, they is asking you this question.
Okay.
How will the
So,
predicted values matches the real data in your study?
so when comparing the predictive performance of the model, we can use RMSE, which is the actual error. So, for example, here, can you see the slides?
Yes, we can see.
So, for example, here, our best model has 0.1 root mean square error. It means that on average, if the actual nanotoxicity is 4, our model predicts maybe 3.9 or 4.1. But visually, it looks like this. So the points are the actual data. And as you can see, the um, the model, which is this grid, uh, almost perfectly captures the data. The only problem here is because there are several vertically stacked data points. For example, across this part, I think this is 6.5 Ag%. So since there are other metals involved, we get different toxicity values for the same Ag concentration. So the model uh, cannot, of course, since it's a the model cannot have a vertical surface for that. So it adjusts to just the mean, I guess, across these 3 points.
Thank you, Paul. Thank you for explaining it that well. Arpita, I think you have, yeah, she says, thank you. for your explanation. Yeah. Anybody else? Any other question for Paul? We can still take up one more question. Well, Paul, I don't see any more question in the chat box. With this, I would like to thank you very much for your wonderful talk and very much on time and very precise yet very informative. We hope to be in touch. Thank you very much. Thank you. And I hope we get more work done collaboratively with SRMIST and you and with your collaborators. Thank you. Thank you.
Yes. Thank you, ma'am.
I now welcome our next speaker, Dr. Ojodomo J. Achadu from Shizuoka University, Japan. Dr. Ojodomo has a PhD from Rhodes University, South Africa. He is currently a JSPS postdoctoral fellow in Shizuoka University in Japan. He has nearly 45 publications with about 400 citations. He works on nanobiosensors designed for infectious viruses. And I believe it's a very important topic after this entire year of pandemic. So I welcome Dr. Ojodomo to deliver a talk on molybdenum-based quantum dots nanotubes and integrated 2D nanostructures for virus detection. Over to you, Dr. Ojodomo.
Okay, good day, everyone. Can you hear me and also see my screen?
Yes,
already?
We can hear you. We can also see your screen.
Okay,
yes.
Thank you so much. And it is my pleasure to be here today to present my work very briefly to you. And it's been an interesting conference so far. So I want to also share my work, which is on virus detection. So I will be taking you through briefly what we are doing with molybdenum-based nanomaterials, quite very briefly. So, and also thank you for the chair of the session for the kind introduction and good introduction. Thank you so much. So, this is my affiliations. I mean, so far, the places I have been to. So currently, I'm at Shizuoka University under the JSPS fellowship, postdoctoral fellowship. I had a brief spell at the University of Bordeaux in France and all these other places that I've had the pleasure of working with some great minds and researchers. So I'll briefly give you an introduction, which is on molybdenum nanomaterials. Molybdenum materials, not very new as such, but then they're finding new applications or new synthesis pathways or new new ways for them to be harnessed and also used in different applications. So now currently we have emerging molybdenum quantum dots, which have found very good application and optical properties, which is similar to what you can expect with the conventional noble metal nanoparticles, such as gold, silver, and the likes. But then the advantage of this material is that they can have or behave, have plasmonic effects or plasmonic surface plasmonic resonance, and also exhibit some good semiconducting properties, which we have, and also have some very good structures, which is a single layered few crystalline structures. And they can, most importantly for optical-based detection or applications, is the fact that they have very good optical resonances, as you can see here in the visible region and also in the NIR region. Some researchers have also, based on surface functionalization and tuning, can also extend the plasmonic resonance into the far IR regions. So this material exhibits some very interesting crystalline structure, the alpha, beta, and the gamma crystalline structure based on the arrangement of the crystals. So this material, these properties make this molybdenum material very interesting. And also these materials are quite cheap compared to gold nanoparticles. They're very stable compared to these other noble metal nanoparticles. And also we can also prepare some sophisticated morphology of this material based on advances in nanoscience and nanotechnology that we're currently involved with. So what makes this material very interesting is the fact that, as you know, optical properties or optical applications such as Raman, it's actually an inelastic sort of process, or a surface enhanced Raman scattering, whereby the light is being absorbed. Okay, in normal Raman, for instance, you have your molecule. They can actually absorb light or energy, and also they get the energies are they get excited, and the energies can actually lose this energy and go back, and there's a vibration of the bonds, which leads to Raman signals. But then the problem with this normal Raman is the fact that the scattering of the light is quite small. It's quite small, and also they can be consumed when the materials can also undergo some photo relaxation or different relaxation processes, such that you don't see the distinct signal. So it makes it difficult for you to actually use normal Raman to fully characterize some molecules or materials. But then it has been observed that in the presence of materials such as gold, silver, this phenomenon was accidentally discovered. You can have this distinct Raman, or the scattering being more enhanced or be more intense. And as I show you, and this is due to the phenomenon of the localized surface plasmonic resonance that we see in noble metal nanostructures. So if you have your normal molecule, which will otherwise not undergo some significant or distinct Raman signal, being caught up in the presence or in between plasmonic nanomaterials, you can see quite significant enhancement in the Raman signal of such material, which is the basis for the sex-based application and processes. And what is involved here is that we have electromagnetic enhancement phenomenon, or the charge transfer, which could result directly, electron transfer directly from the surface of the plasmonic material to the molecule in question. Or we can see the electromagnetic field effect, which is due to the surface plasmon, that can result in electronic coupling and also enhance the signal of the molecule. So using this very principle, CES materials have been nanotags, what we refer to as Raman nanotags, have been designed. And this slide just shows what you can expect by the conjugation of 4-mercaptobenzoic acid, which is known as a Raman reporter because it has a distinct Raman signal that originates from the aromatic ring and also from the carboxyl bonds, and also the different bonds on top of it. So this is my work, whereby the conjugation for mercaptobenzoic acid, the Raman signal, as you can see, is not very, very good or not very distinct because of the fact that, or what I explained earlier, the normal Raman for molecule tend to be quite small in intensity. But then we see in the presence of molybdenum quantum dots, based on their plasmonic coupling with this 4-mercaptobenzoic acid, we're able to see the increase in the signal, in the Raman signal. So these peaks are now quite noticeable, and also this kind of preparation where you conjugate a Raman reporter molecule, such as smaller dyes, 4-mercaptobenzoic acid or rhodamine 6B, 6G, and the rest. In the presence of this plasmonic material, you can see this kind of signal enhancement. And this kind of material is what we call Raman or CES nanotags, which are used in different applications. So I will show you a very typical example of a Raman principle or Raman CES application in biosensor design. So basically, what happens in this setup is you prepare your CES nanotags, and this nanotags is actually containing a plasmonic material, which is the gold in this case, and also you need to attach them, coat them around with a reporter. And so this reporter is what carries, what can give some Raman signal this way, as shown here, where we can record two distinct peaks. This is actually for MBA that I showed earlier on. then you can, in order for you to bring closer the CES nanotags to capture your analytes, you need a biotargeting agent, which is in this case is an antibody. So what happens in this system typically is that you can have a substrate, a solid substrate, which is shown here, where you can carry out your Raman measurements. So this substrate was actually functionalized with an equally functionalized magnetic functionalized gold nanoparticles to lead to aid magnetic separation, just like what you see here. So so in the presence of another equally targeting antibody that can actually capture the virus or your target analytes, as the case may be, you can create or form a sandwich nanostructure between the substrate material, which is in this case magnetic gold nanoparticle, which is labeled with the specific antibody for this virus, and also the corresponding CES nanotag, which has been also labeled with virus. You can form a sandwich structure. So after magnetic purification and separation of this whole immunocomplex from sample matrix, you can have this material you can drop cast them on a substrate, which could be a smooth glass, or in some cases, we can also functionalize the CES substrate, which I will show you earlier on. Then you can take your direct CES measurement and you can generate a signal like this, which will, so the correlation, the indirect relationship between the analyte concentration and the Raman signal is the fact that the more virus you have, the more sandwich immunocomplex you form, which means the more nanotags are going to be present on this CES substrate. And the more you have the signal of the reporter being increased based on the amount of the reporters that is going to be conjugated or trapped in the sandwich nanostructures. So we actually have used this same principle to fabricate a nanosensor based on norovirus detection using the 2D graphene material or substrate. So instead of using a blank or bare glass substrate, we fabricated a graphene substrate, whereby, and this is due to the fact that graphene also has some contribution to Raman enhancement. So using molybdenum nanocubes, we were able to synthesize novel materials, novel plasmonic property of molybdenum, which we made use of the cubic nanostructure, which can generate more intense Raman scattering based on edge effects. So firstly, we characterized the novel material that we had produced, which was based on molybdenum nanocubes. The term image here shows us that we obtained some cubic materials based on molybdenum within the range of 100 nanometers thereabout. Then this is a STEM image that shows us a bit of when we actually grafted some magnetic nanoparticles on the surface of on the cubes. So we performed different experiments to characterize our material, but then most importantly is we can also see from the EDX or the STEM, the EDX mapping or the STEM mapping, that we have magnetic nanoparticles scattered around the structure or around the nanocubes. So with this characterization, we're able to have a little bit of confidence that we have the material that we have prepared. Then we further did some morphological or structural characterization using XPS, whereby we were able to observe all the expected peaks based on the elemental and atomic composition of the material. So then further, the design and application of the nanocubes is now being explained here. So this process, I'll take you through quite briefly. We prepared the nanocubes via a hydrothermal process, whereby we use a molybdenum precursor in the presence of ferric chloride, which is of course the magnetic precursor. And via the endothermal synthesis and also the oxidative reduction of the molybdenum precursor and hydrothermal process, which we controlled, which we optimized and controlled the different temperature, different ramp time of the hydrothermal treatment and everything, and finally achieving the whole cubic nanostructure. So the whole process comes from the synthesis, then antibody labeling, which is the norovirus antibody that is specific to the norovirus. We labeled it on the surface of the magnetic molybdenum nanocubes. So after the labeling, we assure that the nanocube that is labeled with the antibody can bind strongly to our target virus. Next, we went to the preparation of the substrate. So rather than use the best glass substrate, which is the conventional way of measuring, doing your CES measurement, instead we decided to functionalize the glass substrate by drop casting and drying single layer graphene on the substrate, the glass substrate. Now we equally conjugated antibody that is also reactive or specific towards the target virus on the surface of the graphene functionalized substrate. So now this acts as our capture substrate, whereby we initially, or from the beginning, before the whole process, capture the virus before we add the CES nanotags. So one of the hotspot engineering concepts that we are deployed in this work was, rather than the usual method of conjugating the CES reporter or the Raman reporter to the nanocubes themselves, we rather conjugated them on the graphene substrate. So this was actually aimed at giving us some first-hand experience, rather than having some direct enhancement from the nanocubes that is being attached. We decided to attach the Raman to the substrate so that we can have an effective dual effect. One from the target nanocube, which will be sandwiched between the substrate and between the virus and the substrate. Then also the contribution from the graphene substrate to the CES effect or the CES signal of the reporter. So with this, we're able to pursue or generate some so this actually based on the immunocomplex characterization, whereby the formation of this substrate, we're able to confirm that yes, we can actually form this substrate in solution, as well as if we have them on the solid graphene functionalized, 2D graphene functionalized platform. So we're able to generate some 10 images whereby we can see some of the graphene nanosheet, not very clear, but then we have a little bit of signal or visualization of the virus. But then this is the virus is not very obvious based on size consideration. We have about 2 microns or thereabouts different nanosheets of the graphene nanosheet, then also the very bigger size. The virus size is around 30 nanometers relative to the nanocubes. So this spectra here is the Raman spectra that is generated for the black line shows us the graphene substrate alone without the reporter or the other CES nanotag, and also in the presence of the nanocubes, or in the presence of the nanocubes and also binding the reporter, which is the 4-MBA, we're able to see some little bit of bump and enhancement that due to the graphene Raman signal and also the corresponding 4-MBA signal, which is shown in the red line. So with this Raman spectra, we're able to see that yes, we properly functionalize the surface of the graphene substrate with our reporter system. So then by varying the concentration of the virus, we're able to record a different intensity in the CES reporter, and this we attributed to the catalyzed improved Raman scattering that is experienced by the reporter due to the additional capture of the CES nanocubes, of the CES nanotags, which is the molybdenum nanocubes in this case. So we were able to use, we used 2 different peaks of the reporter to generate a calibration curve, and we can use this calibration curve to quantify the amount of the neuro VLP, the virus-like particle, which we had used in testing the operational concepts of the biosensor. So in addition to using the reporter alone, we decided to also use a system whereby we did not conjugate the 4-mercaptobenzoic acid reporter to the substrate. Rather, we used the characteristic D and G band of the 2D graphitic substrate as the capture substrate and also as well as the reporter. However, we see that the sensitivity of using this 2D graphitic substrate alone without the Raman probe, the sensitivity is not as high as that of the reporter. And this is not perfect. This is due to the fact that the Raman reporter, based on their small size, they can experience more higher plasmonic coupling compared to the 2D graphitic nanostructure. And also, this is also due to the fact that the 2D graphene substrate itself contributes to the sense enhancement of the smaller reporter. So it is expected that the synergistic contribution to the sense effect or to the Raman scattering signal of the reporter molecule from both the molybdenum nanocubes and also the graphene substrate would contribute to larger or higher sensitivity, as we see from our results. So we can also construct calibration plots based on the D and the G bands of the graphene oxide substrate that is used in the biosensor design. So then to also test the applicability of this system, we actually conducted the detection of this norovirus in our clinical fecal samples. The norovirus were extracted from different clinical samples, fecal samples, and we collected different different concentration, and we're able to quantify with this very system. Then we also compare, for validation and all that, we compare the sensitivity of our method with commercially available ELISA kit for norovirus detection. And we found that, yes, we can comparatively detect higher or more sensitive norovirus. The system can actually be used to detect sensitively norovirus compared to some to the tested ELISA kit. Then also, one of the very important aspects of the biosensing is the fact that we want our our system or design biosensor to be highly specific for target analytes. And this, in the presence of other virus and VLPs, we're able to see that the target virus performed excellently well. So therefore, giving us confidence that our virus can specifically work for the target virus. So this also is actually inspiring because the systems seem to be quite universal. We just need to fabricate the sex nanotags and also the substrate with the appropriate targeting agent for specific analytes. So which means by the use of a specialized antibody, we can also use this system to detect all kinds of viruses with very good sensitivity. So next, which is also important, was to test the reproducibility and uniformity of the substrates. This is actually quite very important in CES because one of the drawbacks of CES technology is the issue with reproducibility. And therefore, it makes it difficult. We were able to confirm a very good reproducibility of the whole system, the detection, and also the substrate in the first place, because we can have quite a repeatable and consistent measurement at different spots. So in order to also fully understand what happens with the plasmonic properties of this material, we have done some simulation using the finite element method of this material. We're able to see that, yes, the catalyzed CES effect that we experience is because we're able to bring together, via the sandwich immunocomplex formation, 2 or more CES nanotags to form a very good localized CES hotspot region. So as customary with CES nanotags, we're able to simulate what happens, what is the intensity of the set of plasmonic plasmonic activity resonance or the electromagnetic field distribution that is generated at different laser excitation. Then we also simulate what happens when these materials are close together or where they are far apart together. So we have also developed a study whereby we engineered some hotspots for this CES nanotag based on molybdenum, whereby we're able to control the distance between two analytes or between the two CES or between the two nanotags so that they can be close together. So we found that if you have the closest possible spacing or nano gaps between the your nanotags, which is based on molybdenum in this case, you can have more hotspots generated compared to when they are very far apart. We actually use simulation to prove the catalyzed enhancement via sandwich immunoassay protocol for molybdenum trioxide. So next, I want to briefly also talk about my work again, which is based on hybridizing molybdenum quantum dot with another 2D system, which is a graphitic carbon nitride system. So I will not draw much on this because of time. So we've actually used this system to detect influenza virus. And what we simply did, in this case, not CES that was used, we actually use fluorescence as spectroscopy for the detection here. We conjugated antibody for influenza A virus, H1N1, that can also recognize H3N2. We conjugated them to the graphitic carbon nitride and also the molybdenum trioxide quantum dots. So we form a sandwich immunocomplex by interacting them in the presence of the influenza virus. So by this sandwich immunocomplexing, we're able to induce some kind of localized plasmonic coupling to significantly enhance the fluorescence of the graphitic carbon nitride QD. So using also the molybdenum trioxide, using their plasmonic coupling with the excitation spectra or the emission spectrum of the graphitic carbon nitride, we can see that we experience some kind of plasmonic enhancement in the emission of the graphitic carbon nitride. So this kind of properties or this kind of interaction can also lead to the concentration dependent increase in the signal that was experienced, because now in the presence of different amount of the virus, we can actually bring two or more of these materials of the molybdenum material closer to the surface of the graphitic carbon nitride quantum dots, so that this will experience some kind of enhancement based on the plasmonic resonance and coupling interaction. So based on this, we also did some selectivity tests and found out that this system, by using the H1N1 antibody to functionalize this system, we experienced little or no significant interference from other virus and VLP. So this system was used for the sensitive detection of H3N2 clinical sample that's been H3N2 extracted from clinical samples. So this whole study, our study here so far have shown that molybdenum-based nanostructures, we've used the plasmonic nanocubes, we've also used some nanosheets. We're currently also trying out some nanorods and also developing some smart chemical system based on these nanomaterials, based on molybdenum oxide quantum dots, to continue in the design of highly sensitive biosensors, and also in some cases in the current trial for specific targeting of a SARS-CoV-2 virus, which has been a global issue till date. So we also see that the interaction between this material and also a plasmonic and a 2D planar structures can actually lead to unprecedented sensitivity in the system. So because of the fact that this material are biocompatible, they're cheap and very friendly, we can use them in future for implantable and wearable sensors, and also have very good important application in vivo biosensing. So I would like to thank Professor Enoch Whitepath, who is my host and supervisor here for this wonderful time here. I also wish to thank the JSPS and Japanese government for the opportunity to carry out my research in Japan here for 2 years. And I also thank you, the organizers, for the conference. Thank you for listening to my talk, and I will be happy to take your questions. Thank you so much.
Thank you very much, Dr. Ojadomo. very, very interesting talk. And now we can take up a couple of questions. Yes, any question from the audience? You can either text it or unmute yourself and ask question directly. While others are texting, I have one quick question from you. Like,
okay.
I could see that you have worked on enveloped and non-enveloped viruses. So like norovirus and H1N1.
Yeah.
So is there a difference you're seeing, like when you are starting with SARS-CoV-2, like an enveloped virus, which is having a bilipid layer, will that have some kind of interactions? Because the first study you showed that with other virus compared with norovirus, the sensitivity was pretty low for other viruses. So can you throw some light on this?
Can you come again with your question?
Yeah, like with enveloped virus and non-enveloped viruses having a bilipid layer, will that cause some kind of hindrances for your sensor that you are coming up? Or that is showing some difference? You are seeing some difference based on the virus structure?
Well, actually, not specifically, because the only difference that it can cause in this place is if we are targeting using the virus itself as we're monitoring the signal that is generated from the virus. So in this case, we only need to have create some specific interaction between the virus and also between the nanotag and also the virus. So for the question that what you just asked, we found some studies have actually used this concept to discriminate between the envelope virus and the non-envelope virus by using the signal of the viruses themselves, or the signal of the protein structure or the protein structure of the viruses, to actually observe the Raman enhancement. So, but then this actually leads to a lot of signal overlaps and irreproducibility. So therefore, you need to use some kind of statistical approach to discriminate between the signal of the virus or the protein of the virus, or also some tags, or also even the nanotags themselves. So that leads to additional studies. Yeah.
Thank you.
You're welcome.
Yeah. And anybody else would like to question or would like to suggest something, or any curiosity in association with the biosensors? No, I don't see any messages from anyone.
Okay.
No, I think everybody was really overwhelmed with your talk. Very, very interesting and excellent papers that you came up with. And
thank you so much.
Yeah, it was a pleasure to have you with us today. And thank you very much for coming and delivering this interesting talk. I believe we will be in touch with you, and we have a lot more to do in the near future. And with this, our session is coming to an end. Dr. Alagiri, you have a few points to be mentioned.
Yes, ma'am. Yes, ma'am. Okay, so I thank invited speaker and Professor Paramita Chakrabarti Madam for sharing the session. So now I request the participants to join the keynote session at 12:30. So thank you all.
Okay, thank you.
Thank you. Stay safe and have a great day. Thank you.
All right. And you too. Bye.